Let's do an example with electric fields using a problem that's in the book, and I'm going to illustrate it here. So we have two charges. There's a charge that's Q1, it's negative 50 microcoulombs, and Q2 is positive micro 50 coulombs. They're separated by 52 centimeters. And we have point A, which is directly above charge 2. And we want to know the electric field in this area at point A based on charge 1 and charge 2. And you notice that you have this vector going straight up. That's the electric field at A due to charge 2. And we have this vector pointing back towards charge 1. That's the electric field at point A due to charge 1. And then we have the resultant E sub A, which is the resultant vector. And we have the vectors here for point B, which is equidistant between these 2 points, but above the axis. Now notice the distances, like we said, the two charges are separated by 52 centimeters. That means it's about 60 centimeters between point A and Q1. We have 30 centimeters and distance between Q2 and point A. And then for point B, it's basically an isosceles triangle. So this is 40 centimeters here. Now we can calculate this angle that's shown at point A. That's 30 degrees. And we know the angle EA2, this angle here, that's 90 degrees. This angle is based on this isosceles triangle, and we're going to have this theta is the arctangent. It's going to be negative of 30 centimeters over 26 centimeters. And that's going to be equal to negative 49.086 degrees. And since the symmetry, this is an isosceles triangle, I have this angle theta, the magnitude of the angle at above is going to be the same, so that's going to be 49.086 degrees. It's just the difference in the negative signs. The vector pointing down is going to be negative, the vector pointing up is going to be positive. So now we can write down our information. So we have Q1 is equal to minus 50 microcoulombs. Q2 is equal to 50 microcoulombs. Theta A1 is equal to minus 30 degrees. Theta A2 is equal to 90 degrees. Theta B1 is equal to minus 49.086 degrees, and theta B2 is 49.086 degrees. Put in our distances. Okay. And now it's very similar to what we did with the forces. We just have to keep track of everything. So electric field at A in the x direction is going to be K of the charge times the absolute value of Q1, because we already figured out the angles, RA1 squared, cosine of theta A1, and then we're going to have the electric field equation, like so. And that's going to be 9 times 10 to the 9th Newton meter squared per Coulomb squared. I'm going to factor that out. And I get 50 times 10 to the minus 6 coulombs over the distance RA1, so it's going to be 60 centimeters squared. Actually, we got that. We're going to do that in meters since we're putting everything into base units. Plus and our distance A2 is going to be 30 centimeters. Oh, I forgot the cosine. You're all probably hitting the screen. Cosine of A1 minus 30 degrees. Oh, forgot I factored that out. So now I'm doing 50 times 10 to the minus 6th coulombs over distance A2. It's going to be 0.3 meters squared. Cosine A2 is going to be 90 degrees. And that equals 1.082 times 10 to the 6th newtons per coulomb. Do the same thing with the y direction. Just remember it's in the y direction, so we change to a sine. Again, I'm going to factor out that k constant. And I have A1 is 0.6 meters squared, sine. And sine A1 is negative 30. Okay. Put in my last one in here. And that's going to be 4.371 times 10 to the 6th newtons per coulomb. And I can find the total electric field at A is going to be the square root and the magnitude is just going to be the Pythagorean theorem. It's just a lot of writing, isn't it? And you gotta make sure that you keep everything correct. Try to put units in here. And put that all together, and the magnitude is 4.503 times 10 to the 6th newtons per coulomb. And the angle is going to be equal to the arctangent of the y value over the x. And that equals 76.102 degrees. So there's my magnitude and angle. And if I look at the drawing, you can see that this is about 76 degrees at this angle right here. Now I'll let you look at the notes to see about how to calculate for point B, but notice that because of the symmetry, the resulting electric field points directly to the right. And that will be true of any point along this y-axis when there's symmetry of these two particles, symmetry and opposite. You will get this electric field vector pointing straight to the right along this vertical line in between those two charges. So this is how we can calculate electric field using components. Now let's look at how to calculate the electric field using vectors.